let's look at a couple of more problems on calorimetry. This is an easy topic, like I said, and once you understand the basics, you can solve any kind of problems related to calorimetry. So here's a problem. We're now talking of a calorimeter of mass 50 grams containing 200 grams of water at 20 degrees centigrade, right? So we have a calorimeter weighing 50 grams, having 200 grams of water, and the whole unit is at 20 degrees centigrade, right? Now what is done is, in this, 20 grams of ice, 20 grams of dry ice at 0 degrees centigrade is dropped in the calorimeter. So the calorimeter along with its contents is at 20 degrees centigrade. Ice at 0 degrees centigrade is dropped in it, right? And the whole unit is stirred well, is mixed well. Now, what really happens is, the final temperature of the system, the final temperature of the mixture becomes 11 degrees centigrade. That means the calorimeter along with its water, that is contents, and the ice that is added to it, which was originally at 0 degrees centigrade, the whole thing now is at 11 degrees centigrade, right? It's given that the latent heat of fusion of ice, okay, we want to calculate the latent heat of fusion of ice, given that the specific heat of the material of the calorimeter is 0.095, right? So when I add ice to it, what will happen? The calorimeter along with its contents, which is at higher temperature, will lose heat. Ice will gain heat. Initially, the ice which is at 0 degrees centigrade, it would prioritize that heat to convert ice to water, to melt ice to water. Only after the whole process of melting ice to water is accomplished will there be an increase in temperature of ice, right? So that would be latent heat. So that would be sensible heat. So initially there would have to be latent heat provided to ice to convert into water, and then that water at 0 degrees centigrade would convert into water at 11 degrees centigrade. So then ice that was of a certain mass, 20 grams, how much heat has it consumed? How much heat has it gained in the process? One, of course, 20 mass into latent heat, right? That's the heat required to convert ice to water at 20 degrees centigrade. And then I have 20 grams of water at 0 degrees centigrade, 20 grams of water at 0 degrees centigrade converted into 20 grams of water at 11 degrees centigrade. So if I take the specific heat of water to be 1, then the sensible heat required would be mass into specific heat into 11. So then 20L plus 220 calories is the heat that ice would have got. And where would it have got that from? From the calorimeter along with its contents. So calorimeter would have lost heat. Calorimeter and the contents of the calorimeter, that would have lost heat because it was originally at 20 degrees centigrade and now it's the whole thing is at 11 degrees centigrade, right? So then the calorimeter alone, look at the calorimeter alone. So that's 50 grams of calorimeter. It's given that the specific heat of the calorimeter is 0.095. So then heat lost by the calorimeter is going to be what? Mass into specific heat into 20 minus 11, which is drop of temperature. That's the heat lost by the calorimeter. And the 200 grams of water that is contained in it is like 200 mass into specific heat into drop of temperature. That's the heat lost by the water that was originally contained in the calorimeter. And this whole thing, heat lost is heat gained. If I apply that principle of calorimetry, then, and if I solve for L turns out to be 81.14 calories per gram as the latent heat of fusion of ice. Now, simple problem. I hope you're all fine with it. Let's look at another problem. So this next problem is about heat that is supplied at a uniform rate to a piece of ice, right? We have a piece of ice at a certain temperature. We do not know whether it's at 0 degrees centigrade or at some minus theta degree centigrade, right? We do not know, right? Whatever be it, there is a external source supplying heat, calories per second to ice at a certain rate, right? Now, the melting starts to happen 2 seconds later. It's given that the melting of ice doesn't happen instantly, it happens 2 seconds later. That means initially the temperature must have been driven to 0 degree centigrade. Initially, therefore, the temperature must have been less than 0 degree centigrade, and I assume that the initial temperature was minus theta degree centigrade, right? Now, so only in the first 2 seconds, the heat that is supplied starts to increase the temperature, and the melting starts after that. That means in the first 2 seconds, the temperature goes from minus theta to 0, and there is participation of sensible heating. There is participation of sensible heating. Now, so in the first 2 seconds, what happens? First 2 seconds at the rate of Q dot calories per second, the heat supplied is 2 Q dot, and that has taken m grams of ice, that originally was m grams of ice with specific heat 0.5, and increase of temperature minus theta to 0 is like increase of temperature by theta. So mass into specific heat into theta, in 2 seconds the heat supplied is 2 Q dot, right? In the next 20 seconds, what happens? The heat supplied is going to be 20 Q dot, and that's going to be mass into latent heat, which is 80 calories per gram, right? Because once having reached 0 degree, melting would commence. That would be in the next 20 seconds, and the amount of heat consumed then would be 20 Q dot. Q dot is a constant, right? Calories per second. In 20 seconds, it's going to be 20 Q dot would be mass into latent heat. Yes or no? Now, all that I need to solve for is theta. I divide equation 2 by equation 1. 20 by 2, that makes it 10. And then this by this, m gets cancelled. 80 divided by 0.5 theta. M will get cancelled. This will be theta equal to 16 degrees centigrade. I hope all of you are comfortable with all of this. Very shortly, I'll come up with a few more problems. Bye-bye until then. See you.